Hello and welcome back. So we are looking at the Johnson-Lindenstrauss lemma and then trying to argue why that lemma is true and basically trying to prove the statement of that lemma. Let me just recall where we are and quick recollection of the lemma itself. So of course we know the lemma by now. So you have n points in Rn in Rd where d is like large, and then the lemma says that or at least the version of the lemma that we are looking at says that if you apply the transformation 1 by square root kr, where r is a k cross d matrix where every entry is Gaussian distributed with mean 0 and variance 1, then you end up mapping the n points in Rd to Rk, where the pairwise distances are preserved with very high probability of between these endpoints. So that's the statement of the lemma. When I say preserved, it means that if we have any x minus y squared here, so f of x, or rather let me put it this way, mx minus my's norm squared is at most 1 plus epsilon x minus y squared, and at least 1 minus epsilon x minus y squared for any x, for all x comma y in the original set S. Let us say this is the set S of n points. So that's the lemma, and to prove this or to understand this, we were trying to look at some probabilistic properties of the vector after it gets transformed by the transformation. I should also say here, when I say m itself is 1 by square root kr. That's the transformation. So we said last time that you take any u in Rn and then apply 1 by square root kr, you get, let's say, v is 1 by square root kr, and we said that the expected value of the norm of v squared is norm of u squared. That is, the lengths are preserved in expectation by this low dimensional transformation or a random projection. So the lengths are preserved in expectation, but we want to see how much, how can we say something more in terms of high probability. That's the question that we were asking, and for that we looked at this this small definition that we made of this variable x, which we defined as square root of k v by norm of u. And the reason why we made that is because when you do this, x is square root of k v by norm u. Of course, x is in Rk because v is in Rk. But not just that, x is a very well known distribution, random variable, which comes from a very well known distribution. In fact, x in Rk in this case is Gaussian distributed with mean 0 in Rk. When I say 0 vector, it means that it's like k components with 0, and then the variance is just the identity, right? This we argued last time by looking at the covariance matrix and so on. And then what this helps us do is understand the high probability event that we care about in terms of x as opposed to in terms of v and u. Specifically, we put down the following. We said that if I care about the bad event, that after I do this mapping from u to v, the length of u squared is greater than some 1 plus epsilon times the length of u squared. So this is the bad event that we want to bound the probability for. Now this is exactly same as, and this we saw last time, and this is where we were the end of last time. This is exactly the same as the probability that the length of x squared is greater than or equal to 1 by epsilon times k, and that's not too hard. That just comes simply from the definition of x. The length of x squared is just k norm v squared by norm u squared. You just do some taking things from one side to other side, you get this, right? So basically the probability of the bad event, why is it bad? It's bad because the length of v squared is more than 1 plus epsilon times k, and we want to preserve it up to 1 plus epsilon times k. Well, we cannot preserve it always, and then we are saying that, well, at least can we say that the chance that something goes wrong is small. Let us say the chance of this, maybe if we somehow bound this by 0.001, which means that then 99.99% of the time the length of v squared is going to be within 1 plus epsilon times the length of u squared, right. So, that's a very high chance, right. So, now we want to answer that question, right. So, what is the chance that, is this a rare event or something bad can happen? With, let us say, 50% of the times the length of v squared is going to be greater than or equal to 1 plus epsilon u squared, then that is not really a very strong statement to make, right. So, because most, I mean, it is like random chance that it is either distances are preserved or not preserved, and that is not a good place to be in, right. So, now for that we need to understand this, right. So, and now what we are saying is that you can either analyze this bad events probability directly, or you can equivalently analyze the chance that the length of a multivariate Gaussian vector, squared length of a multivariate Gaussian vector is greater than or equal to 1 plus epsilon times k. We can analyze that as well, right. So, these both are the same things, and that is a great thing, because now we had some question in mind, and then we have reduced that to a pure probability question about multivariate normal vectors, and we have very good handle over that, as we will see, and we will use properties that we already know about multivariate normal distributions to bound this probability of this event happening. So, just to give a sense for so what we are going to do today is understand this better, and just to give a sense of what we are really talking about here. Remember, x is Gaussian distributed with mean 0 and covariance I, that is x is, let us say, x1 x2 till xk. You can equivalently think, well, if the covariance is identity, then it means for a Gaussian, I mean, it is equivalent to saying that there is no correlation between any of these random variables, and for Gaussians no correlation implies independence. So, you can in fact think of these as k different independent Gaussian random variables put together as a vector form, right. So, now this is x. Now, let us first ask the question, what is the expected value of x squared, right. So, what should we expect, right. So, I think that is, I mean, when you are doing any probabilistic analysis, expectation gives you a rough guess as to what kind of values are we talking about. Of course, the variance will tell me how bad it is spread around the expected value, but at least we should kind of get the expected value properly first, right. So, what is the expected value of norm of x squared? Well, let us calculate this. This is just the expected value of sum over I equals 1 to k xi squared, linearity of expectation, sum of expectation of xi squared. Well, what is the expected value of xi squared? By now we are experts in this, we should know this. So, xi is Gaussian with 0 mean, variance 1, and we know variance of a Gaussian with 0 mean is same as the expected value of Gaussian squared. So, this is just the variance of the Gaussian of xi, and because these are all independent Gaussians with variance 1, so this is just 1. So, which means that I am summing up over k such Gaussians. So, the expected value of x squared is k. So, what is it telling us? That so if x is the length squared of a Gaussian random vector in k dimension, then we are expecting it to have a value of k, right. And now let us go back and ask, what is the question that we are asking? On an average, this value is going to be k, but now what we are interested in is, well, what is the chance that it is greater than or equal to 1 plus epsilon times k? Let us say epsilon is 0.2, then we are asking, well, on an average I know that it is k, but then what is the chance that it is greater than 1.2 times k? Now we are already seeing that, you know, because the average is k, now it's critically going to depend on how it is, you know, distributed around the average, right. So if it has a large variance, then probably, you know, the chance that, you know, norm x squared being greater than 1 plus epsilon k is large. If it is, if it falls down faster around the mean, then probably this is a, you know, this event will not happen too often, 1 plus epsilon times k. So we need to find out which of these is the case. So we need to understand this quantity better, but at least we know that, you know, the x on average at least we are good, right. So on an average this is not going to be too bad, this will be k, but you know, what is the chance that it deviates significantly from the average? That's the question that we are asking. And now you naturally see that what we basically want is a concentration bound, right. So because we want to know how well the length of a squared length of a randomly picked Gaussian vector concentrates around its mean, which is k, right. So that's basically what we are asking for. So all the tools of concentration bounds that we have seen before are at play, right. So because we can kind of use them to argue something about this. So the way we will argue it is as follows. So now we want to understand, want to bound the probability that norm x squared is greater than or equal to 1 plus epsilon times k. Well, there are many probability bounds, concentration bounds that we can use. You can use Markov, you can use Chebyshev, you can use whatnot, right. So all of these are valid concentration bounds. It's okay to use Markov because norm x squared is always a positive random variable, so Markov is at play. We can use Chebyshev also because k is just the expected value of norm x squared. So basically we are asking, it's 1 plus epsilon times the expected value. So that's directly a Chebyshev kind of a quantity that we can use. What we are going to do is, you know, something that will lead us to a stronger concentration bound. It's what is called as a Chernoff-style bound. We will see how to do that here. But all I wanted to say is, we can use Markov, we can use Chebyshev, but what we are going to do is we'll get a stronger bound using what we will do now, which also uses Markov in a different way, as we will see. Okay, so let's try this, right. So what we are going to do is, this might seem odd at first, but if you have not seen this before, but this is a very standard way to prove concentration bounds in what is called as a Chernoff-style bound. Chernoff. So Chernoff inequality is another popular inequality, and we'll do something like that here as well. Yeah. But let's do this from first principles. So basically, now if an event happens, right. So think of this as x is drawing multivariate Gaussian at random, and then I am asking what is the chance that this thing happens. Now if this happens, right. So the event that this happens, if this happens, that is if norm x squared is greater than 1 plus epsilon k, then it also has to be the case that, you know, e power lambda norm x squared is greater than or equal to e power lambda 1 plus epsilon times k. Right. So if x square is greater than or equal to 1 lambda is greater than or equal to 1 plus epsilon k, then e power lambda x squared will be greater than or equal to e power lambda 1 plus epsilon k. That's just a mathematical fact, right. So if a is greater than b, e power lambda a is going to be greater than or equal to e power lambda b. And similarly, e power lambda a lambda norm x squared is greater than e power lambda 1 plus epsilon k, then I can take the logarithm on both sides. Logarithm is a monotonic function. So lambda x squared will be greater than lambda 1 plus epsilon k. Lambda is positive, so I can cancel lambda. So norm x squared will be greater than 1 plus epsilon k, which means that both these events are equivalent, right. So whenever the first event happens, the second also happens. Whenever the second happens, the first also happens, which means that the probability of the first happening is exactly same as the probability of the second happening. Now, why would anybody want to do that? So that's the Chernoff-style, way of bounding this, and we will see why that is a useful thing. Now, typically, now this guy is a positive random variable, right? So it's a non-negative random variable. Well, it was a non-negative random variable earlier also. Norm x square was also non-negative because it cannot take negative values. It's a square. Now when we are doing e power something, that will definitely be a non-negative random variable, which means we can apply Markov's inequality. Now, what is Markov's inequality? If you remember Markov, so if what the chance that a random variable is greater than some quantity is at most the expected value of that random variable divided by that quantity, right? So, which means that I can bound this probability by expected value of e power lambda norm x squared divided by e power lambda 1 plus epsilon times k. Why is this true? This is simply by Markov. I am just applying Markov's inequality. I am treating this whole guy as a random variable. This is my x. Remember, Markov is probability of x greater than a is at most expected value of x divided by a. So this was my Markov, and then I am thinking of this whole thing as my x random variable. It is a random quantity because x is random, because x is multivariate Gaussian. So any function of it is going to be random. So this is the random variable, and so I am applying Markov directly here, right? So I get this. So now then it means now we need to study this quantity here. So let's study that quantity a little bit carefully. So this is equal to, this previous quantity is equal to e power, I am just expanding out this norm x squared, sum over I equals 1 to k xi squared divided by e power lambda. So these are all algebraic expressions. They might seem bigger, but then the basic idea is not too complicated, right? So every step is easy to follow. Okay, so this happens, and now what can I write this? So this is e power, which means this is e power lambda x1 squared plus lambda x2 squared plus lambda x3 squared dot 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 plus lambda xk squared, right? That's the expectation in the numerator, right? So let me actually write it down so that it becomes easy for us to follow. E power lambda x1 squared plus lambda x2 squared dot 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 lambda xk squared divided by, anyway this is untouched, this is anyway there. So now this is the e power sum of a bunch of things. I can write it as the product of e power bunch of things, right? So I can write this as the expected value of product of I equals 1 to k e power lambda xi divided by e power lambda 1 plus epsilon k. This is okay. Nothing, this is just exponentiation's property that I have used. Now let us look at this quantity. So it is a product of e power lambda xi, but remember every xi is independent of every other xj, right? So you have x1 through xk, but then this is a random Gaussian vector, standard Gaussian vector, but then you can think of it as each of these quantities independently a random Gaussian variable, right? So standard Gaussian, standard normal variable. So which means that the expectation of their product is just the product of their expectation. So I can write this further as product of I equals 1 to k expected value of e power lambda xi divided by the same thing, nothing changes in the denominator. Okay, so so what has happened? So why are we doing all this? So what have we gained by doing this? So we started, remember, we started with asking the original bad event, and the original bad event is same as this event here, and then we did a e power lambda thing, and then we are doing some algebra, and we have finally got something like product of I equals 1 to k e to the expected value of e power lambda xi divided by e to the lambda 1 plus epsilon k. Now, what have we gained, right? So, now this guy is Gaussian with 0 1, and we are asking the expected value of e power lambda that Gaussian. Now, again, if you have taken like a basic probability course, you can already recognize that this is in fact what is called as the MGF, or like a moment generating function. So the reason why I am bringing this up here is that because xi is standard Gaussian, all its properties are already well studied, which means that one of the properties is the moment generating function, which by taking derivatives and so on, you can get all the required moments. Moments are e power x, expected value of x, expected value of x squared, expected value of x cube, and so on and so forth. All of those values can be obtained by this moment generating function, and that is why this is a powerful function in general in probability, and it is very well understood for specific distributions. Popular distribution, most of the popular distributions we understand the moment generating function, and the most popular distribution is the standard normal distribution, for which this is very well studied. So, I am going to use a fact about standard normal distributions moment generating function, or the expected value of e to the lambda xi when xi is standard Gaussian. I am not going to prove this, I am going to assume that this is a fact that is already there. I mean, it is a fact that is already there, and we are going to assume this fact for our purposes. So, in fact, this value is very well understood. This is in fact something like this. This is 1 by 1 minus 2 lambda square root, right. So, that is in fact this value, right. So, for any standard normal variable. So, this quantity is understood well, right. So, this expected value of e power lambda xi is just square root of 1 by 1 minus 2 lambda. It is not too hard to prove. I mean, you need to do, you can explicitly write down the integration and then solve this as well, but we are not going to worry about that here. Let us assume this is true. Of course, divided by e power lambda 1 plus epsilon k still is there. Now, this is the same value independent of which Gaussian that we are talking about, for all the k Gaussian. So, it is the same quantity that I am multiplying k times. So, in fact, this numerator then is just I can write it as 1 by 1 minus 2 lambda power k by 2 divided by e to the lambda 1 plus epsilon k. Okay, so what have we got? We have somehow got a bound that does not have any expectations or any random variables on the left hand side, right. So what are we essentially saying now, right. So, what is this quantity? So, basically we are saying the probability that of the bad event is at most this quantity, right. So, remember the bad event was norm v squared greater than or equal to 1 plus epsilon norm u squared, and that is where we started, and then we are saying this bad event is less than or equal to whatever this quantity on the left hand side is, right. So, which seems like a very unwieldy quantity at this point. So, this is true for any lambda greater than 0, right. So, this is the quantity. Now, we have the power to choose the lambda here, right. So, there is nothing stopping us from choosing a specific lambda, any lambda. For any lambda greater than 0, what we are saying is that this right hand side is in fact an upper bound for the bad event. I can put any lambda. For instance, I can choose lambda equals 3 or 4.1, whatever it is, right. So, it's still an upper bound. Of course, we would want to choose lambda which is which will make this upper bound Do we want it to be as small as possible or as large as possible? Think about this, right? So we are saying the probability of a bad event is upper bounded by some quantity. We don't know the exact probability of the bad event because that's too hard to find out. But we are saying using concentration inequalities, it cannot be more than some quantity, right? So now I want to make a statement about how much is this quantity, right? So now I know that for any lambda, I'll get a quantity, right? So if I fix lambda, of course, if I have to fix k, I have to fix epsilon, but then if I fix lambda also, then I'll get something in terms of k and epsilon. Now I have the power to fix lambda, right? So should I fix lambda such that this quantity is as large as possible or is it as small as possible? What do we want? If you think about it, we want the probability of the bad event to be not too much. So we want to choose lambda such that this is as small as possible. So which means one way to proceed would be to, think of this whole thing as a function of lambda and then try to differentiate this with respect to lambda and then set it to 0, choose that lambda for which this value is as small as possible. That's one way to proceed. We will do a slightly different way. So which will get us to the similar conclusion, but that's the idea, right? So lambda is a free variable and then we are going to somehow tweak it as we go along. Okay, so what happens next, right? So I'm going to rewrite this whole thing slightly differently. So there is an exponentiation in the bottom, so I'll write the above thing as also as exp. So I'm going to write this as an exp of log of this quantity, right? So which means that this is log of 1 minus 1 minus 2 lambda power k by 2 minus, well, if I take the denominators exp to the top, so then that will become minus lambda 1 plus epsilon k. So this the first term, the numerator is obtained by cancelling this expand log. So that will just be 1 by 1 minus 2 lambda power k by 2, which is the numerator. Now I have an e power, in the power I have this quantity minus e power. So this is e power minus lambda times 1 plus epsilon k, which is just the denominator going to the numerator, right? So which we know, this is again some algebra. So this is k, so there is a k here, so log of something power k by 2, I can bring the k down, so that will become k times half log, all I am doing is just algebra, right? So there is nothing magical happening here, minus lambda times 1 plus epsilon. Okay. So these are all equality, right? So there is nothing much I am changing here. Now one can do a Taylor series expansion of log and then upper bound this guy using a quantity which I will state now. So this is exp of k, so this is not equal to anymore, so this is less than or equal to exp of k times this half log 1 by 1 minus 2 epsilon. So one can do a Taylor series expansion of logarithm and then we can upper bound this as lambda plus 2 lambda squared. This stays this way and then whatever earlier was there stays, minus lambda epsilon. I have just opened up the bracket here, that still stays, right? So this quantity came from, you can try this out for yourself. So this is a Taylor series expansion for log. Now for and small enough lambda, I think lambda less than 1/3, so something like that, this will be true, right? Now then these two guys cancel out. So what we are left with then is, this is exp k times 2 lambda squared minus lambda epsilon. Okay, so that's where we are. Now it's still an upper bound. I've just did some more calculations. So instead of taking the derivative, we could have taken the derivative with respect to lambda here itself, treating this as a function of lambda, but then it looks like a messy function. But this is this guy is a much easier function, right? So now I want to ask, for what choice of lambda is this value going to be the smallest, right? So now I can take the derivative of, think of this as a f of lambda is 2 lambda squared minus lambda epsilon, right? So then if I take the derivative f dash of lambda is 4 lambda minus epsilon, set this to 0, I get lambda is epsilon by 4. I plug, so basically for the choice of lambda is epsilon by 4, this value becomes the smallest. Remember, this is a convex function, right? So it's a square, and this is a linear in lambda. So this whole thing is convex. So now this is a minimum then at lambda equals epsilon by 4. I plug it back in. So f of epsilon by 4 will just be 2 lambda squared, which is epsilon squared by 16 minus lambda time, which epsilon by 4 times epsilon squared. So this is epsilon squared by 8 minus epsilon squared by 4, which is just minus epsilon squared by 4. That's right. So this whole thing, the smallest I can make this quantity is, this is for lambda equals epsilon by 4, and I'm going to assume epsilon is not too big such that all the Taylor series choice, Taylor series is true only for small enough lambda. I'm going to think of epsilon as small enough such that lambda is epsilon by 4 satisfies the Taylor series as well, which is usually true. So then this is basically x of k minus epsilon squared by 4, which is a neat looking expression.